Hello, everyone. It's my great honor to be here at OpenInfra in Korea. My name is Peng Wang from OceanBase Global. Over the past years, we've also heard from the AI workloads are evolving, from retrieval-augmented generation to semantic search to document Q&A systems. But while these applications are exciting, we are faced challenges with a larger scale, low latency response, and keep the architecture simple and reliable across clusters and even cloud providers. So today, I'd like to share how OceanBase is tackling these challenges. By bringing vector search and AI workloads natively into a distributed SQL database, fully running on a Kubernetes cluster. Before we dive into today's topic, let's have a quick look at who we are and the kind of real-world demands our system is built to handle. OceanBase is a distributed database founded in 2010, and we've spent over 15 years on high availability and high performance. Today, we have more than 1,000 employees and serve over 2,000 customers worldwide across industries like fintech, e-commerce, and telecom, and manufacturing, and others. Some of our customers worldwide, just like Starbucks, McDonald's, P&G, HSBC, and others, all trust in OceanBase to empower their mission-critical business. Okay. Next is the first part of this topic, RAG application. RAG means Retrieval-Augmented Generation. And we will explain why our customer choose OceanBase and why only OceanBase can do what they do. Use a RAG example to demonstrate OceanBase's ability to accelerate AI applications. Here is an example. Of an intelligence Q&A system. In this system, the users search for coffee shop, and he input, please recommend a coffee shop within 500 meters that has an average consumption of less than $8 per person. And after analyze this natural language input, the system returned some recommended results. And based on the analysis, there are three kinds of queries. Filtering within 500 meters is a special query. And the average consumption of less than $8 per person is scale query. And determining which restaurant is primary coffee shop based on the restaurant's name or type is not easy. So we need to vectorize the restaurant's feature and perform vector query based on the data. In the conventional architecture, there are three kinds of databases to handle these different queries. And the system calls API to access, to find the restaurant's name in the vector database, such as Mavis and Fizz, and use PGSQL, MySQL to search for restaurants within 500 meters and the average consumption of less than $8 per person. And the AI application needed to merge and sort the results returned by the three different databases. But this implementation is quite complex. For example, the restaurant's name returned by the vector database could be a large number of records, and filtering these records based on the result returned by the PGSQL and the MySQL could consume a significant memory and result in performance limitation. So we choose to use OceanBase replace these three different databases. And OceanBase support multi-model data types, such as structured data, JSON, GIS, and vector, and others. In the unified data platform, the customer can perform hybrid query in OceanBase. And in this example, in OceanBase, we can transfer the natural language input to a single hybrid query SQL statement. And the SQL statement includes 3 different queries: a spatial query, scale query, vector query. And in the second part, let's introduce OceanBase hybrid query capability. As mentioned in the previous part, OceanBase supports multimodal data. It supports structured data such as int, string, and arrays. It also supports KV pairs, spatial data, vector data, converted from the documents, audios, and images. With this, OceanBase offers an integrated architecture that unified data storage and unified data access with a SQL query, NoSQL query, and AI query. Let's introduce OceanBase HTTP capability. In the conventional architecture, if the customer wanted to perform OLAP queries, they need an ETL tool to do data synchronization from OLTP database to OLAP database. It means there are 2 different databases in the system, as well as 2 different data sites. And the data synchronization could result in data latency and the potential risk of data inconsistency. On the other hand, OceanBase is a HTTP database. For customer, no need for data synchronization, eliminating data latency and ensuring true real-time data consistency. Next, let's introduce OceanBase AP performance. AP means analytical processing. And we use ClickBench test tool to compare the performance of OceanBase and other analytical databases, such as ClickHorse, StarRocks, and Doris. As the feature shows, OceanBase has the best performance for cold run and hot run. And next, let's introduce OceanBase's feature, vector query. Compared to the normal databases with HNSW algorithm alone, OceanBase combines HNSW algorithm with BQ algorithm. For the same data size, the database with HNSW alone, it needs 1.2 TB memory. But for OceanBase, with the combination of HNSW and the BQ algorithm, it only needs 58 GB memory. It's a 95% memory reduction. For OceanBase, not only is the memory reduction, but it also has strong performance. Compared to the Elasticsearch version 9, OceanBase gains 16% higher performance. Next, so let's use VectorDB Bench to compare the database performance between OceanBase and other vector databases, such as Mavis and Elasticsearch. From these 2 features, we can say OceanBase also has the best performance under different data specifications. Okay, in the third part, let's have a brief introduction to the integration of Define and OceanBase. Define is an open source platform for building AI applications without coding. And it relies on 3 different databases: pgSQL for meta storage, Vivid for vector data storage, and Redis. But maintaining these three different databases is quite complex, from large scale to resource isolation. In short, DeFi is powerful for AI workloads, but the database architecture is the bottleneck. So we choose to use OceanBase to replace these three different databases. After that, the whole system, the whole database service, can automatically recover within 8 seconds. And it also has online scaling capability. And in OceanBase, with multi-tenancy, a database cluster can safely serve multiple workloads with strict resource isolation. So instead of these three different databases, DeFi now running on a unified data platform. In the next part, let's have a short interview instruction on OceanBase high availability and low cost. This is the architecture of OceanBase. In OceanBase, the data is distributed across different availability zones. And we use multi-paxos algorithm to keep data consistency across different availability zones. So in this system, if a server node goes down, or even a available zone become unavailable, the whole system can automatically recover within 8 seconds and with no data loss. On the other hand, OceanBase also supports seamless online scaling for both horizontal scaling and vertical scaling. Next, let's introduce how to deploy OceanBase on Kubernetes cluster. In the beginning, we deploy all the availability zones in a single Kubernetes cluster. But depending on a single Kubernetes cluster is risky. For example, it's a single point of failure. Any outage could bring down your entire system, and it also impacts on the upgrades. Since you put everything in one place with no safety network, and it also has high maintenance pressure for operators and engineers because they have to do everything in one place, from data storage to failover. After that, we changed our mind from deploying on a single cluster to multi-cluster. Why multi-cluster makes sense? In multi-cluster architecture, we deploy each available zone independently in a single Kubernetes cluster. It makes the system has true high availability and disaster recovery. Your system can survive even a Kubernetes cluster goes down. And it also supports seamless Kubernetes upgrades. You can upgrade the cluster one by one. And in the long run, it lays the foundation for hybrid cloud architecture, giving you more flexibility and resilience. And this approach is inspired by our customer. Our customer deployed their application across different cloud providers. So they wanted OceanBase to deploy on the same way. After that, our customer has high availability and disaster recovery capability at the cloud provider level. Besides, OceanBase also has strong compression performance. Compared to the normal databases, in OceanBase, data storage cost is reduced by 70 to 90%, as well as TCO is reduced by 70 to 50%. Why OceanBase can do that? Because OceanBase has two compression layers. In addition to the normal compression layer, OceanBase has an extra layer of data encoding, effectively compress the data twice. Okay, in the final part, let's share some customer success stories. The first one is from our customer, Trip.com. Trip.com has two business requirements. The first one is photo similarity search to find similar hotels and speed up the booking process. Next one is identify the cheapest hotel supplier. But in the process, they are facing many challenges. The first one, the data set is massive, and real-time analysis is impossible, and building vector index is too slow. And the customer want to perform hybrid query in the database. So after changing to OceanBase, the customer's system is running stably for over 1 year. And OceanBase offers strong hybrid query capability. And the vector index creation speed improved by more than 4 times. And it also enables real-time analytics. The next case is from Lalamu. Lalamu needs a system to answer drivers' question quickly, whether the question came as image, audios, or long text. Even supporting image search. But they're facing some challenges like their existing database service crashed frequently and lacks hybrid query capability. And vector index construction is slow. After changing to OceanBase, OceanBase provides financial-grade database service, ensuring business stability. And the whole system can automatically recover within 8 seconds and with no data loss. With the combination of HASW and BQ algorithm, OceanBase significantly reduced memory consumption for vector indexes. And the most important is customers can perform hybrid query in OceanBase, a unified data platform. The last one is from our customer, Quai. Quai needs real-time analysis of transaction data, but they are facing high costs. It requires over 400 servers, and managing so many servers and the database instance is extremely challenging. After changing to OceanBase, no data synchronization needed, and enabling real-time analysis, and it saves over 300 servers. And in OceanBase, it also reduces storage cost. So with OceanBase and Kubernetes, OceanBase and Kubernetes, we are not just managing data. We are building a new open infrastructure for the AI-driven future. Okay, that's all. Thank you. Thank you for your time. Thank you.
네, 저희 시간이 조금 남은 관계로 잠깐 Q&A 시간을 가져볼까 합니다. 질문이 있으신 분 손 들어주시면 감사하겠습니다.
Okay, yeah, I think the most key in the RAG systems, from the business, from the database side, I think it's a vector search latency. Yeah, and as we know, compared to other vector databases, OceanBase has better performance on the vector search or vector queries. So I think the search speed is most important for the RAG, in the RAG applications. And this is from the OceanBase. This is from the database side. Yeah, in my own opinion, yeah. Okay.
Is there any bottleneck in the rack latency? Bottleneck?
Sorry?
Which factor do you think is the bottleneck in the rack search time?
For this question, currently I don't have the answer of this question. Maybe we can discuss this question offline. Yeah. Sorry for that. Yeah.